Application: Verifying quadrilaterals squares. Welcome, everyone. Today, we are starting a new subsection focused on the application of coordinate geometry. Specifically, we are going to learn how to use the distance formula as a tool to prove whether a given set of 4 points on a coordinate plane actually forms a square. Now, it is important to remember that in coordinate geometry, simply identifying that a figure is a quadrilateral, meaning it has 4 sides, is not sufficient for a complete proof. To be precise, we must go a step further and use the specific properties of its sides and its diagonals to identify exactly which type of quadrilateral we are dealing with. Over the next few slides, I will show you the exact methods to distinguish a square from other shapes, like rectangles or rhombuses. Understanding the properties of a square. Now that we've introduced our main goal of verifying squares, let's look closer at what actually defines one. First, it is important to remember that a square is what we call a regular quadrilateral. In geometry, regular simply means that the shape is perfectly symmetrical, all its sides are the same length, and all its internal angles are equal. However, here is the challenge. If we only check that the sides are equal, we might accidentally be looking at a rhombus. If we only check that the angles are right angles, we might just have a rectangle. To distinguish a square from these other quadrilaterals, we can't just guess. We must mathematically verify specific geometric properties. To do this, our primary tool will be the distance formula. As you remember from our previous lessons, the distance formula is the square root of the quantity x2 minus x1 squared plus the quantity y2 minus y1 squared. We will be using this formula repeatedly to measure our sides and diagonals to ensure our figure meets every single requirement of a square. Method 1. The sides and diagonals approach. Now that we understand we need to use the distance formula to check specific properties, let's look at our first strategy. This is what I call the sides and diagonals approach. To mathematically prove a quadrilateral is a square, we need to satisfy 2 specific conditions. First, we must show that all 4 sides are equal in length. That is, the length of side AB equals side BC equals side CD and equals side DA. Now, be careful here. If you only prove that all 4 sides are equal, you have only proven that the figure is a rhombus. It could still be a tilted diamond shape. To upgrade that proof from a rhombus to a square, we need a second step. We must also verify that both diagonals are equal in length, meaning the length of diagonal AC must equal the length of diagonal BD. When you have both equal sides and equal diagonals, you have successfully verified a square. We will see this exact logic applied in the step-by-step method in the next few slides. Method 2. The sides and angle approach. Now, while the first method we discussed focused on comparing the diagonals, there is an alternative approach you can use, which focuses on the internal angles of the shape. To prove a quadrilateral is a square using this second method, we need to satisfy 2 specific conditions. First, just like in our previous method, you must verify that all 4 sides are equal in length, specifically, that the length of side AB, BC, CD, and DA are all identical. This step, as we noted earlier, confirms that the figure is at least a rhombus. However, to elevate that rhombus to a square, we need to prove that at least one internal angle is exactly 90 degrees. To do this without a protractor, we use the converse of the Pythagoras theorem. For instance, if you calculate the squares of 2 adjacent sides and find that AB squared plus BC squared is equal to AC squared, then you have mathematically proven that the angle at vertex B is a right angle. If you can confirm both the equal sides and this right angle, you have successfully verified a square. Step-by-step procedure to verify a square. Now that we have understood the 2 different methods for identifying a square, let's break this down into a clear, systematic procedure you can follow every single time. Suppose you are presented with 4 specific points on a coordinate plane, which we will label as A with x sub 1, y sub 1, B with x sub 2, y sub 2, C with x sub 3, y sub 3, and D with x sub 4, y sub 4. To verify if these points form a square, you should follow these steps. First, in step 1, your task is to calculate the lengths of all four sides of the quadrilateral. You will apply the distance formula that we discussed earlier to find the lengths of side AB, side BC, side CD, and side DA. Next, in step 2, you need to compare these side lengths you just calculated. This is a critical decision point. If you find that all four sides are not equal, then you can stop right there. The figure is not a square. However, if you find that all four sides are indeed equal, then you have successfully proven the figure is at least a rhombus, and you must proceed to step 3 to complete the verification. Step-by-step procedure continued. In step 3, we need to calculate the lengths of the two diagonals. To do this, you will apply the distance formula once more, but this time, instead of looking at the perimeter, you are looking across the shape. You'll need to find the length of the segment from point A to point C, and then find the length of the segment from point B to point D. Finally, in step 4, we perform our final verification to reach a conclusion. This is where we distinguish a square from a rhombus. If you find that the length of AC is equal to the length of BD, then you have successfully proven that the quadrilateral ABCD is a square. However, if you find that AC does not equal BD, then you have only proven that the figure is a rhombus, but not a square. Keep this distinction in mind, as it is a very important step in our logical proof. Now that we have finished step 2, where we checked if all four sides are equal, we move on to the most critical part of the process. Real-world example, land surveying. Now that we have understood the theoretical methods for verifying a square, let's apply what we've learned to a practical, real-world scenario. Imagine you are working as a land surveyor. Your task is to mark the corners of a specific plot of land and determine if the area is a perfect square. You have been given the coordinates for the four corners. Point A is at 1, 1, point B is at 4, 1, point C is at 4, 4, and point D is at 1, 4. Before any construction can begin, you must use the mathematical steps we just discussed to verify whether this plot of land truly forms a perfect square, or if it is actually a different type of quadrilateral, like a rhombus or a rectangle. Real-world example, solution. Now that we have our coordinates for the four corners of the plot of land, let's move into the actual calculation. Following the procedure we discussed in the previous slides, our first step is to calculate the lengths of all four sides to see if they are equal. First, let's find the length of side AB. Using the distance formula, we take the square root of the quantity 4 minus 1 squared plus 1 minus 1 squared. This simplifies to the square root of 3 squared plus 0 squared, which gives us the square root of 9, resulting in a length of 3 units. Next, let's look at side BC. We calculate the square root of the quantity 4 minus 4 squared plus 4 minus 1 squared. This simplifies to the square root of 0 squared plus 3 squared, which also gives us the square root of 9, or 3 units. Moving along to side CD, we find the square root of the quantity 1 minus 4 squared plus 4 minus 4 squared. This simplifies to the square root of negative 3 squared plus 0 squared, which again results in the square root of 9, or 3 units. Finally, let's calculate the length of the last side, DA. We take the square root of the quantity 1 minus 1 squared plus 1 minus 4 squared. This simplifies to the square root of 0 squared plus negative 3 squared, which brings us back to the square root of 9, or 3 units. As you can see, all four sides are exactly 3 units long. However, as we'll see in the next slide, we can't stop here. We still have one more crucial step to perform to confirm this is a square and not just a rhombus. Real-world example, continued. Now, let's look at what these calculations actually tell us. Since we found that the length of side AB, BC, CD, and DA are all equal to 3 units, we have successfully proven that all four sides are equal. However, remember what we discussed in our earlier methods. Having 4 equal sides only guarantees that the figure is a rhombus. To move from a rhombus to a square, we need one more piece of evidence. So, moving on to step 2, we must now calculate the lengths of the two diagonals to see if they are equal. So, moving on to step 2, we must now calculate the lengths of the two diagonals to see if they are equal. First, let's find the length of diagonal AC. Using the distance formula, we take the square root of the quantity 4 minus 1 squared plus the quantity 4 minus 1 squared. This simplifies to the square root of 3 squared plus 3 squared, which gives us the square root of 9 plus 9, resulting in the square root of 18. We can simplify this further to 3 root 2 units. Next, let's calculate the length of diagonal BD. We take the square of the quantity 1 minus 4 squared plus the quantity 4 minus 1 squared. This becomes the square root of negative 3 squared plus 3 squared. Since squaring a negative number gives us a positive, we have the square root of 9 plus 9, which also results in the square root of 18, or 3 root 2 units. Notice that both diagonals have come out to be exactly the same length. Real-world example, conclusion. Now we have reached the final step of our calculation, which is step 3, the conclusion. Let's look back at everything we have discovered. In the previous slide, we calculated the lengths of all 4 sides and found that they are all exactly 3 units. We also calculated the lengths of the 2 diagonals and found that both are equal to the square root of 18, which simplifies to 3 root 2 units. Because we have successfully verified that all 4 sides are equal and that both diagonals are equal, we can confidently conclude that the plot of land, ABCD, is a perfect square. This completes our verification process. Common mistakes to avoid. Now, before we wrap up our lesson and look at the final summary, I want to pause and discuss some common pitfalls. Even if you understand the method, these 3 mistakes can easily lead to the wrong conclusion. First, a very frequent error is stopping your calculation immediately after verifying the sides. You might find that all 4 sides are equal and think, great, it's a square. But remember what we discussed in the previous slides. A rhombus also has 4 equal sides. If you don't perform that crucial final step of checking if the diagonals are equal, you haven't actually proven it's a square. Second, pay close attention to your point pairing. When you are working with points A, B, C, and D, you must calculate the sides in their proper sequence, which is a B, BC, CD, and DA. Then, you must calculate the diagonals across the figure, which are a C and BD if you accidentally pick a diagonal and treat it as a side. For example, calculating a B, AC, and a D as sides. Your entire verification will be mathematically incorrect. Finally, watch out for sign errors during subtraction. This is a classic trap when using the distance formula. When you are calculating x sub 2 minus x sub 1, be extremely careful if you encounter negative coordinates. For instance, if you have 2 minus negative 3, remember that subtracting a negative is the same as adding a positive, so it becomes 2 plus 3, which is 5, and then squared, giving you 25. A small slip with a minus sign here can ruin your entire calculation. Keep these in mind as you practice, and you'll avoid the most common traps in coordinate geometry. Key takeaways. All right, class, we have reached the end of our lesson. Let's wrap everything up by reviewing our key takeaways to ensure you have a solid grasp of this topic. First and foremost, remember that proving a square is a 2-step verification process. You cannot stop once you've checked the sides. You must verify both side equality and diagonal equality. To put it into a mathematical condition, a quadrilateral is a square only if side AB equals side BC, which equals side CD, which equals side DA, and at the same time, diagonal AC must equal diagonal BD. It is very important to distinguish between different shapes. If you find that only the condition where AB equals BC, equals CD, and equals DA is true, then you have only proven that the figure is a rhombus. It might not be a square unless those diagonals are also equal. Similarly, if you find that only the opposite sides are equal and the diagonals are equal, then you are looking at a rectangle. Finally, always remember that the distance formula is your primary tool for all these verifications in coordinate geometry. Keep practicing those calculations, and you'll master this in no time. Great job today.